Imagine a molecule as a tiny, flexible structure made up of even tinier particles called electrons. When these molecules encounter electromagnetic waves like light or heat, they can distort. This distortion is called polarizability. It's like squeezing a balloon. The shape changes, but the balloon itself remains intact. This seemingly simple phenomenon plays a crucial role in shaping our planet's climate. Polarizability dictates how molecules interact with different types of electromagnetic radiation. It determines whether a molecule will absorb, scatter, or allow radiation to pass through. This interaction between molecules and radiation, particularly in the atmosphere, is what governs the Earth's temperature and drives the greenhouse effect. Understanding polarizability is key to unraveling the complexities of global warming. It allows us to see how different molecules like water vapor, carbon dioxide, and methane interact with the sun's energy and influence our planet's delicate energy balance. In essence, polarizability provides a window into the invisible world of molecules and their profound impact on the world we experience every day. Dipolar polarizability comes into play when molecules have a separation of charge, creating a positive and a negative end. These molecules, like tiny magnets, are called dipoles. When exposed to electromagnetic waves, specifically in the UHF to microwave region, these dipoles start to rotate and vibrate. Water vapor, H2O, is a prime example of a molecule with a strong dipole moment. In the Earth's atmosphere, water vapor molecules constantly interact with microwaves. They absorb the energy from these waves, causing them to rotate and vibrate. This absorbed energy is then re-emitted in random directions, effectively trapping some of the heat within the atmosphere. Methane, CH4, another powerful greenhouse gas, also exhibits dipolar polarizability. Though it has a symmetrical structure, the slight distortion caused by the presence of 4 hydrogen atoms around the central carbon atom gives it a dipole moment. This allows methane to interact with microwaves, contributing to the greenhouse effect. This dance of molecules with microwaves, governed by dipolar polarizability, is a key player in the Earth's energy balance. It's a constant reminder that even the smallest interactions at the molecular level can have a profound impact on our planet's climate. Water vapor, the most abundant greenhouse gas, regulates Earth's temperature. It absorbs and re-emits infrared radiation, acting like tiny, vibrating springs. This process traps heat, keeping our planet warm enough for life. Without it, Earth would be frigid and inhospitable. Rising temperatures increase water vapor, amplifying the greenhouse effect. Understanding water vapor is crucial for predicting climate change. Methane, though present in smaller amounts compared to carbon dioxide, is a far more potent greenhouse gas. Its ability to absorb and re-emit infrared radiation driven by ionic polarizability makes it a significant contributor to global warming. Like water vapor, methane molecules also possess specific vibrational modes. When infrared radiation interacts with methane, it excites these vibrations, trapping heat within the atmosphere. However, methane's vibrational modes are particularly efficient at absorbing infrared radiation in a region of the spectrum where other greenhouse gases absorb less. This makes methane exceptionally good at trapping heat. Furthermore, methane has a relatively short lifespan in the atmosphere compared to carbon dioxide. While this might seem like good news, it also means that reducing methane emissions can have a more immediate impact on slowing down global warming. This makes targeting methane emissions a crucial aspect of climate change mitigation strategies. From leaking pipelines to livestock farming, human activities are the primary drivers of increased methane concentrations in the atmosphere. Understanding methane's role in the climate system and finding ways to reduce its emissions is vital for mitigating the impacts of climate change. Feeling the heat in infrared. Ionic polarizability is crucial in how molecules interact with infrared radiation, the energy we feel as heat. Exposed to infrared, ions move like dancers swaying to music. When infrared matches vibrational frequencies, molecules absorb energy, causing bonds to stretch and bend. This absorption is what we experience as heat. This process traps heat in the Earth's atmosphere, contributing to the greenhouse effect. Section 6, carbon dioxide, the invisible threat. Carbon dioxide, a colorless and odorless gas, is often called the invisible threat of climate change. Human activities, primarily the burning of fossil fuels, have significantly increased its concentration. Carbon dioxide absorbs and re-emits infrared radiation, trapping heat within the Earth's atmosphere. Reducing carbon dioxide emissions is crucial for mitigating climate change. Section 7. Electronic polarizability, ozone's balancing act. High above Earth's surface, in the stratosphere, lies a protective layer of gas called ozone. This ozone layer, though relatively thin, plays a crucial role in shielding life on Earth from the sun's harmful ultraviolet radiation. Ozone's ability to absorb UV radiation is governed by electronic polarizability. Unlike dipolar or ionic polarizability, which involve the distortion of entire molecules or the movement of ions, electronic polarizability focuses on the movement of electrons within an atom or molecule. When UV radiation strikes an ozone molecule, it causes the electrons to momentarily shift their positions, absorbing the UV energy. This absorption prevents harmful UV radiation from reaching Earth's surface, protecting us from skin cancer, cataracts, and other health problems. However, ozone's relationship with global warming is complex. While it protects us from UV radiation, ozone itself is a greenhouse gas. This means it can absorb and re-emit infrared radiation, contributing to the greenhouse effect. The concentration of ozone in the atmosphere is influenced by both natural processes and human activities. Understanding the delicate balance of ozone's protective and warming effects is crucial for predicting future climate change. Section 8. Total polarizability, a symphony of interactions. Total polarizability represents the combined effect of all types of polarizability, dipolar, ionic and electronic within a molecule. It's like a symphony orchestra, where each type of polarizability plays a unique instrument, contributing to the overall sound. This combined effect determines how a molecule will interact with the entire spectrum of electromagnetic radiation, from low-energy radio waves to high-energy gamma rays. For greenhouse gases, total polarizability dictates their effectiveness in absorbing and re-emitting infrared radiation, ultimately influencing Earth's temperature. Water vapor, with its strong dipole moment and ability to form hydrogen bonds, exhibits high total polarizability, making it a powerful greenhouse gas. Carbon dioxide, with its linear structure and double bonds, also possesses significant total polarizability, contributing to its role in global warming. Understanding total polarizability is crucial for accurately modeling the climate system. It allows scientists to predict how changes in the concentration of greenhouse gases will impact Earth's energy balance and future climate. Section 9. Closing the spectral windows, a warming planet. The Earth's atmosphere acts like a window, allowing some of the sun's energy to reach the surface while trapping some of the outgoing heat. Increasing greenhouse gases are like drawing curtains, closing the spectral windows through which energy can escape. Each greenhouse gas absorbs and re-emits infrared radiation, creating unique absorption patterns. As concentrations increase, the atmosphere becomes saturated, making it harder for heat to escape. This leads to a buildup of heat, contributing to global warming. Section 10. Understanding polarizability, a key to our future. Polarizability, a seemingly abstract concept, holds the key to understanding our planet's climate and the challenges posed by global warming. It allows us to peer into the microscopic world of molecules and comprehend their profound impact on the macroscopic world we experience every day. From the dance of water vapor molecules with microwaves to the ozone layer's absorption of UV radiation, polarizability governs the interactions between matter and energy that shape our world. As we grapple with the urgent need to address climate change, understanding polarizability becomes crucial. It allows us to model the climate system accurately, predict the impacts of increasing greenhouse gas concentrations, and develop effective mitigation strategies. By comprehending how polarizability influences the Earth's energy balance, we can make informed decisions about energy consumption, technological innovation, and environmental policy. In essence, understanding polarizability empowers us to become better stewards of our planet, ensuring a sustainable future for generations to come.